I think it is time to have our keynote speaker, and it is my extreme pleasure to introduce Alex Smola, who is a VP and Distinguished Scientist at AWS AI. Now, Alex, I mean, if you know, I think, the book Learning with Kernels, I think is an excellent book who has, taught a generation of machine learning people mostly about kernels. And I will say that's the best introduction I have seen about functional analysis and what it can do in machine learning to people who are not pure mathematicians. You can look at, Alex is, one of the most, accomplished person there. You can look for his accolades. I will comment some on among the things that I was fortunate to have experience working with him. He's the kind of person who you can have extremely technical discussions on theory, math, randomized algorithms, and at the same time, he can go hour-long on some of the bit tricks to make things efficient. You can expect call from him over the night and talk about some of the cool randomized algorithms to make COVID testing efficient, right? And he's some of the very few person who, even at this stage, where I don't know how many you are managing, but he at this stage still codes, right? And is very particular about, he can sniff that your code is inefficient and they are missing certain cycles. So, it has been pleasure working him, and it is a great honor to introduce a mentor, a colleague, a friend, Alex. Please take it over.
So many thanks for those kind words. I don't think I can live up to the expectations that I should just created. That coding thing, yeah, I wish I had more time for it, but yeah, otherwise you get rusty. But obviously I can't hold a candle to my engineers. They are way better than I am. And a lot of the work that I'll be presenting today is really done by the team, and I'm just the person who talks about it here. Namely, how do you actually design an AutoML system? And I'll use AutoGluon as an example, but feel free to, copy and adopt any of the techniques in there, or, well, help us and join the fray. Okay, so why do we bother, right? And why is Alex, who's at some point written lots of theory papers, talking about an AutoML system? So the thing is, the market has changed. So Andy Jassy announced that apparently Amazon's going to hire over 50,000 new tech people next year. And that brings us to, around 275,000 tech and corp jobs, next year. Now, and part of the problem is that machine learning competency is becoming a key technique for essentially everybody in computer science. So it's no longer just the purview of, a select few, and then you invite your friendly machine learner and he or she solves the problem for you. But it's really something that everybody needs to know, just like they need to know quicksort, really. Now, the problem is North America produces less than 400 PhDs in AI per year. The rest of the world, obviously, quite a bit more, but it's still a trickle compared to, the demands of just a single company. And if you add up all the companies, you would easily end up an order or two of magnitudes higher. So, okay, 65% of all PhDs join industry. The rest, fortunately, goes on and teaches more. So there's hope. But even if you look at the CS undergrads, it's only 30,000 per year in North America. So we have this huge supply problem where, okay, sure, we can assume every new fresh graduate has at least some passing knowledge of machine learning, but what about everybody else? And so you might think, okay, well, maybe this is getting better and everybody's becoming a computer scientist. And I would argue the growth has been at most linear, not super linear. So these are stats from last year. I don't know whether it's still accurate, but basically the only way how we can really make machine learning available to a lot of people is by lowering the bar. So, and I think the community has come a very long way. So in 2010, basically implementing a large linear model is PhD level homework, for instance, at CMU or Berkeley. And if you can build this for, at a very large scale, then you can make $10 to $100 billion easily in revenue at companies such as Google, Facebook, Twitter, wherever. But basically, this is what was driving a lot of the large advertising models. Then around 2017, with deep learning frameworks and so on, while implementing a computer vision network is, PhD level homework, been there, done that. And then, services like recognition, Google Photos, Pinterest, Snapchat, ByteDance, all those places started using computer vision in very non-trivial ways in their products. So, it's clearly becoming more available. Now, by 2021, you can actually implement a Q&A NLP system as undergrad homework. Why? Because you use something BERT pre-trained and then a couple of modifications. And there's basically a lot of things by now hidden, not just in deep learning frameworks, but in libraries. So for instance, if you want to build a classifier that's probably competitive with what most of us, including me, could do off the shelf, you need 3 lines of code. You import tabular predictor from AutoGluon, you train the predictor, and you run fit. So if you will, it's 1 line, and the rest is just overhead. We're not the only ones. There are other AutoML tools out there. Maybe their API requires 4 or 5 lines, but basically the bar has been lowered. And what this means is the tools are now really a lot easier to install. So for instance, in the case of AutoGluon, you can do a pip install, it's on Git, you can have a deep learning container. Then there is the entire Hugging Face zoo with, I think by now over 18,000 models. There's Tim, which does that for computer vision. And there's half a dozen other zoos like that. So that's great, but you still need to know how to use those models. So for instance, how do you deal with covariate shift? A lot of people, if you tell them about covariate shift, this is the first time they actually hear it. How to scale things, how to serve things. In other words, we are a little bit in a situation where, we still need to teach people how to use machine learning in the right way. Now, using machine learning is hard. And it's hard even for very smart people. So for instance, if you get conditioning wrong, then you arrive at Simpson's paradox. This is probably one of the really famous examples. What happened, I guess everybody recalls, but just for a refresher, the admissions rates at UC Berkeley in the 60s were such that the admissions rates for men were higher than for women. And that seemed very, very wrong. And so actually, they looked into this and they found that the conditional admissions rate, as in conditioning on the subject, the admissions rate for women were at least as high, if not higher. At least there was no sign of discrimination. But what happened is that women tended to apply for the more competitive subjects, which just so happened to be arts and languages, whereas the less competitive subjects, such as engineering or math, that's where a lot of the men applied and they got in. Okay. Slightly more recently, so if you design the wrong benchmark for, fairness in vision, then you can become a Netflix movie star. Or if you're a big tech company, then, that big tech company, and again, names are here omitted because I don't want to embarrass anybody in person, they can still struggle significantly with machine learning training beyond SGD. And even a performance engineering team at a very big tech company may struggle with configuring distributed optimization appropriately. And I'm not saying this gleefully as in, haha, and I'm smarter or we are smarter, whatever. No, it's just hard and people can screw up, and I've probably done that myself, right? At the same time, automation is hard. Like the machine learning zoos are full. So 18,000 models in Hugging Face, means probably for whatever problem you have, you will find a pre-trained model. The question is, which one of those 18,000 is it? Then network architecture search is really expensive, but actually you may not want that in general. Maybe just finding the right network is okay. And, if, our friends at Google Brain kindly come up with a new network architecture, well, then, yeah, okay, that's great for the world. Large model training is very expensive. Even AutoML can be very costly. So some cloud systems can easily use hundreds of hours where maybe an hour would be more appropriate. So basically, a lot of the pieces are there, but actually using them jointly, efficiently, is still very hard. So I'm going to use this analogy and probably beat it to death, is it feels a little bit like we're building all those components, right? And we then tell the users, okay, well, this is great. Now go forth and build your car from it, or your scooter, or whatever it may be. But actually, that's what the users probably want instead. They probably want to have a car, and they just want to go and pick from the right car. I would actually go further. That's not really what they want. They want this. And I guess the picture has become quite infamous. That's a driver asleep while his Tesla is on autopilot and hopefully doesn't crash into the next wall. So what we basically want is systems that are as automatic as can be, that will keep us safe and that will do a good enough job. Doesn't have to be perfect, but just has to get us there safely. So let's look at reality. And things are encouraging. So this is on, some Kaggle competition, and basically 3 lines of AutoGluon will get you to the second place on the Mercari dataset. So that's pretty nice because, out of over 2,000 teams, we get the number 2 spot by doing exactly nothing really. There's another data set, and this was a live competition. So otherwise you could say, yeah, you guys just gamed it. No, this was actually, and you can see that our submission is, a bit older than some of the others. And we got the number 8 spot with doing exactly nothing. And with a little bit of tuning and adjustment, well, we get the number 2 spot, right? So this is quite impressive, because it basically means that an automated system is capable of going toe-to-toe, well, not necessarily beating, but at least being pretty competent relative to people who are trying really hard to do really well. Okay. Now, you could say, Alex, you're just cherry picking. And yes, of course, I'm cherry picking, right? So if you look at more Kaggle data sets, you can see that, there are a couple of data sets where we, blow everybody else out of the water. But there are also cases where AutoML doesn't do so well. The only thing you should probably look at is the black, asterisk tends to be further on the left. And so the lines are different data sets, thus Kaggle challenges, and the columns are the percentile rank on the leaderboard. So this isn't like a loss function or whatever. It's just like, how much better than other engineers are we doing, right? And so a percentile rank of 0.5 means that, we do as well as the median engineer. Now, maybe the median engineer on Kaggle isn't terribly good, but what we found in practice is most novice engineers cannot beat AutoGluon. So what we actually did is we had AutoGluon compete against novice engineers just freshly trained in machine learning. And basically 1 or 2 out of over 700 engineers were able to surpass it. Everybody else was worse. As a matter of fact, what we've done based on this information is we've changed the way how we teach machine learning in Amazon. we no longer, at least for the quick intro, emphasize so much, how to design various algorithms, but more on how to use it and how to use it correctly, as opposed to designing their own algorithms, because, well, they will not be able to beat what you can do automatically. Now, if you think, okay, it's just tabular, no, actually you can do more than that. Here's another data set. There we actually got, to the top position. So, this all looks, I think, super encouraging, right? Because what I've shown you so far is a lot of screenshots where, okay, using AutoGluon beats everything else. And, so you could say, well, yeah, we're there, right? So are we there? And actually, I would argue that there is a long way to go, and it's an exciting one. So just to reuse the automobile metaphor a little bit further, so there are those 5 levels of automation in self-driving cars. And they go from no automation to driver assistance to partial automation. That's basically when it stays in the lane, to conditional estimation, so it can perform a bunch of driving tasks, but you still need a human override. And yeah, basically the commercial systems are definitely not at level 5, they're at levels 3 and 4. And what you can get in the cheap consumer car is maybe partial automation, so ADAS. So what I tried to do, and I'm not gonna bore you with the specific text, is I just essentially took that description and translated it into machine learning speak. And on the left, no automation. Yes, the human does everything. Driver assistance, the system features a single automated component, for instance, automatic deployment, model monitoring, model selection, and everything else is manual. What's probably more relevant for us is the ADAS equivalent part. The system can perform modeling, training, and deployment. The human still monitors all tasks and can take control at all time. And I would say we are probably somewhere between 1 and 2. So there are isolated pieces where, for instance, deployment is effective. There are isolated pieces where other parts are effective. We don't really have a nice system that goes and covers all of it. So I would say, even if we, got firmly into automation level 2, if you will, that would already be significant progress. And of course, in order to be able to, deploy it in such a way that anybody who is even slightly numeric can use it, we'll probably need to get to levels 3 and 4. Otherwise, we just do more damage than good. Okay. So to just zoom out a little bit to explain, why I think that we have a long way to go. If you look at machine learning automation, I mean, you can probably group it into 4 aspects, and I've probably missed a bunch of other important ones. So the entire DevOps aspect on the slide is a bit weak. But there's basically the entire issue of, building a good model. And most machine learners are very concerned about that, rightfully so, because without the model, you have nothing. But then you also need data. You also need systems to, train, deploy, make sure that things work properly. And lastly, because these systems are built by humans, you need collaboration tools. And I've color-coded my very subjective view of where we are in various pieces. So on the model selection and tuning and validation part, I think we're doing pretty okay. Pre-training, I think it's very encouraging what's happened over the past few years. There's still exciting progress. So green doesn't mean the problem is solved. It just means at least we have something that could be used and it wouldn't do terrible things. Where we are, I think, really weak right now is essentially model monitoring. In other words, once you deploy it, to find out whether things have changed. And I think that's less because we don't know how to do it mathematically, but because it just hasn't been done. Likewise, data discovery, annotation, and so on. these are sometimes very unglamorous tasks. There are a lot of companies in this area. For instance, Snorkel, I think, has done a good job there. There's Trifactor, Data Wrangler. There are lots of other tools that can be used. Some of them are commercial, actually most of them. But basically, dealing with data is still a mess. Same thing goes for just training at scale. And Anshu just, launched his startup to help with training. And I think it's a very exciting plan that he has laid out. And lastly, collaboration tools. And, the most advanced collaboration tool right now, people use Git, or then they, use a collaborative editor within a proprietary system, but it's nowhere near where we really would like to be. So there's still a lot to be done. And I think it's exciting because the redder I think those areas are, the more there's a chance for doing something principled that's meaningful and that actually gets us further as a community. So what I'm going to do over the next block of this talk is I'll walk you through a few pieces of how we got at least as far as where we are right now. And then I'll give you a bit of an outline of where we're going. And I hope that by the end of this talk, I'll have convinced you to maybe join us on parts of that journey. So the first thing that we use is we use fairly extensive versions of bagging. We use stacking against, again, there's a slight twist to that. We ensemble, and then we fuse models. And now, if you think about that, you've heard all of those terms before, and that's not a surprise because in some cases, you actually do prize robustness over the very best tool that works most of the time, but sometimes fails. So for instance, the one thing you never want is you never want to have a system that, fails on your data. So let's actually look at bagging because that will address already some of the failure modes. Okay. So I guess everybody knows k-fold cross-validation, and I am willing to bet you that most of us are not using it consequently in their papers. And just as a refresher, k-fold cross-validation splits the complete data into, k-folds, and then you use, k minus 1 as training and the last fold as a validation set. And so you get those validation estimates, right? So that's pretty nice. And you can use them for, error estimates and model tuning. And after you're done with that, you have to ask yourself, well, what next? And a lot of us, including me, would have done the following thing, namely, we would say, okay, now, learning rate 0.01 is the right thing to do. Let's pick that. Let's now train, a model on the full data set and call it a day. And therein already lies a first danger, because it could just be that the model never really converges on the full data set. Well, it's a slim chance. It's maybe only a 1% chance that the algorithm will not work, but there's a chance. And the issue is that you actually do have, possibly k perfectly good estimates available, whereas you're now throwing them all away and trying to replace them with something that may fail. That's not very fault tolerant and robust. And it also comes with a couple of other issues, right? One of them is, for instance, what you do at the test set. So what turns out to be a much better idea is to really bag things by just, taking all those k estimates, and we actually oversample. So we often, use 2k, 3k with overlapping validation sets. And this now gives you a much better degree of certainty about the model. It actually gives you some uncertainty estimates, namely just the variation on per prediction. And on top of that, it gives you some variance reduction. So it works a lot better. And it's one of those really simple, dumb tricks that we've known over for decades. And we just, I think, never really took as seriously as we should have. Okay. So then the next thing is ensembling. And if you look at any winning machine learning competition submission, it's not pure. And I do remember the great amount of frustration that I had when I saw the prize-winning competition from Netflix. And we looked at it as like, yeah, and they're throwing everything in the kitchen sink at the problem. You know, it's not a clean, pure solution about, you know, where you can talk about exchangeability of matrices and so on. It's just a mess. And as a theorist, this is supremely unsatisfactory until you start embracing the mess. So as a practitioner, what's the most embarrassing thing that can happen to you? It is if k-nearest neighbors actually beat you. Now, this should not happen, but it can happen in 1% of all cases, and you still look stupid in that case. Why? Because k-nearest neighbors are actually non-parametric and they're pretty robust. And you know, Anshu and others have designed a lot of super efficient algorithms for fast lookup. So yeah, they actually can be made faster. Now, an equally embarrassing thing is if, you know, you get beaten by a tree. Again, it's non-parametric and robust and it's ancient technology, but sometimes it's okay. And if you gradient boost decision trees, it works surprisingly well. So if you use cat boost or XG boost or any of the other boosting algorithms, they're not bad. Now, of course, there's, you know, the best of, you know, 2021 using some very advanced deep network. And of course, you could also throw your favorite kernel method at it because, yeah, why not add it to it? But basically, you know, you want to use reasonably good state of the art, you know, with, you know, dropout, batch norms, ReLU, and you can use that to get a pretty good deep network. And in many cases, this is really good. And in particular, the inductive bias is quite different from the inductive bias that you would get from other models. Now, what everybody is tempted to do is to say, okay, Alex, now you've trained on, you know, those 10 different models. Well, tell me what I really should be doing. Tell me the best thing. And the best thing tends not to be that you go and pick, you know, one single model, but the best thing turns out to be to really combine those models. Because yes, if you find the best model, it's simple and understandable. And if it's just a deep network, then you can maybe put that into your, Triton runtime, and you can serve it easily. But it's almost never as good as a combination. So we go and do exactly that, because if we care about accuracy, well, okay, we check out our, ideological assumptions at the door and just, combine. So, and this is pretty much the set of techniques that we combine. So deep nets, nearest neighbors, trees, forest boosting, but you can bring your own model, which is a really good thing, because if you've already done a lot of engineering and solved the problem well, the very last thing you want is that you get a performance regression just because you switch to an AutoML system. So, of course, if you're a little bit theoretically inclined, you might wonder, why does this ensembling actually work? And let's say I have three models A, B, and C, and maybe I have even some nice nested hypothesis class. So let's assume they're not pathological. Then if I take a convex combination, well, what happens is that now the convex hull of all those models tends to be a lot better behaved than every individual model, right? And so that's one of the reasons why ensembling over different models with different inductive biases can actually help you do really well. Okay. Now, if you think about it, what I just told you about is let us design a linear model on the outputs of a lot of base learners, if you will. Okay. So, yeah, linear models are interesting, but can we do better? And as it turns out, yes, we can. So this gets us to the next, step of this, namely stacking. And this is the part where I think we deviate rather drastically from everybody else. So if you think about it, the outputs of any of those base learners, right? So let's call them model 1 through model n, can be used as features and then, combined, right? So if I just perform ensembling, then I'm just taking the outputs from model 1 through model n, I'm combining that as a linear function, and then I declare this the final output, okay? But what you could do is you could use those outputs of those various models jointly with the input, concatenated into one longer vector. And now, rather than trying to invent some very peculiar, odd linear function of this, well, we have nonlinear functions at our disposal, right? I mean, these are exactly the models that we trained on, and we just now train on the outputs of those models. Okay? So probably most of you will have a nagging doubt that in a moment, because this looks like we're training on the labels, right? But bear with me for a moment. What it really means in terms of algebra is, our first layer, xi, the first layer is just, the original data xi, so that would be x0, so if you will, the input data a of xi. And by the way, you can use bagging to, replace fj of xi with the bagged consensus estimate from multiple folds. So this way you have less variance among those features in the training set. And for the second layer, well, what you do is you basically concatenate the input of the first layer with the output of the first layer, and you keep on doing this. And well, basically we use like 2 or 3 layers. Now, I've drawn this in a way that it should be supremely easy to see what this mirrors, namely DenseNet, right? So in DenseNet, and this is an architecture that at some point won a prize at CVPR for being the best architecture. It's basically an extension of ResNet. Turns out not to work as well as one would hope, because most of the benefit in that paper was through some very, very talented training of the network. Nonetheless, in spirit, that structure works quite well. Namely, you just iterate and compose increasingly large inputs based on the original inputs and the outputs of the previous layers of your stacker. Okay. And so this is the point where the alarm bells should go off for most statisticians, namely, hey, isn't Alex just training on the labels? And as a matter of fact, we try not to. And so let me clarify what the we try not to means. So what we do is to compute the function estimates at location xi, we train on all the data, but the fold that contains the label yi. And then we use the predictions there as the features to be added. And as such, at least in the first level, the estimates are conditionally independent of the labels at that point. Okay. Now, what does happen, though, is that the features at other locations, right, they are not independent of the labels at that point. So basically, for fold 2, the estimates there will depend on the labels on fold 1, and the same thing is true for folds 3 to 5. So therefore, if you keep on stacking further, you do get some label leakage. And you can actually trigger that by just essentially training with random features. And you will find out that after 2-3 levels of stacking, you get, zero validation error. And of course, since it's, random, you'll get random performance on the real test set. So both in theory and in practice, there is label leakage once you go above one level of the stacker. If somebody has a good idea on how to ameliorate this, we would very much like to know and to hear from you about it, because this way we would be able to stack quite a bit beyond 2-3 layers. But in any case, it's not bad. So because after all, let's have a look at, does this work? So these are numbers from about 6-7 months ago. We are currently running the benchmarks again for the final JMLR version of the AutoGluon paper. And the short version is nothing really has changed. Everybody has gotten a little bit better. And basically what you can see is that we win in many cases. So let me explain a little bit what we're logging here. And these are two different data sets. One is for Kaggle, and the other one is for the AutoML benchmark. And champion means that, the corresponding system does better than anybody else. And then the wins and losses are relative to AutoGluon. And basically, so for instance, teapot and a 6 wins means they're 6 times when it's better than AutoGluon. And out of those 6 times, in 5 times, it's actually the very best model, right? So champion, that number is always less than the number of wins. What you can also see is that a lot of systems actually tend to fail. We also fail once. I mean, in the latest version, that no longer happens because, of course, you go back, try to identify what the issue was, and you fix it. But part of the reason why we fail a lot less, and the specific numbers don't really matter. I mean, we just picked a bunch of metrics because we wanted to make sure that, no matter which metric somebody wants to know, we still get a reasonably consistent story. But back to why do we fail a lot less? Well, it's because we have this model combination. So we bag across folds and we ensemble across methods. And now for AutoGluon to fail, all methods would have to fail across all folds, right? And the chances for that are fairly slim. Whereas if I have a system that critically relies on all the components working, or at least one algorithm to work, across all folds or something like that, then, the failure probability is a lot higher. So what we're doing is the equivalent of, how you would design a RAID array for hard drives where, if a single drive fails, it's not so bad. In our case, it's basically, we need catastrophic failure for AutoGluon to fail. I want to draw your attention a little bit to the last column, because this is something that I've seen a lot of benchmarks getting wrong, or in sometimes somebody comes up with a new AutoML system and gaming it. It's the runtime. So AutoML systems are time bound. In other words, I have to be able to say, well, give me the best answer in 4 hours rather than give me the best answer. And the reason is simply that, well, all the AutoML systems get better if you give them more time, as in almost all, and I'll show you that on another figure. And so therefore, giving one AutoML system a lot more time than the other one simply leads to one system sometimes getting better performance where it really shouldn't. Okay, let me just show you the same data, but now as a graph, as a plot here. Basically, the baseline is, loss on test data at scale to 1, and the various colors are basically other systems and how they fare relative to AutoGluon. And you can see, well, we don't always win, and in some cases, we lose rather badly. So for instance, on shuttle and KR versus KP, we do very poorly. But overall, yep, in pretty good shape. Now, back to the time constraint part, and that will become important shortly. So what we did is we looked at AutoGluon GCP tables in H2 AutoML and AutoScaLearn and tplot and AutoWeka, and we ran it with a 1 hour constraint. And then we ran it with a 4 hour constraint. And we basically looked at the times when the 4 hour system, worked better than the 1 hour system, or when it worked the same. And the last thing you want is a situation where if you give it more time, things don't really get better. And the AutoScaLearn numbers are, well, so these are numbers that are probably about 10, 11 months old. AutoScaLearn Mark II has improved, and it looks more favorable now, but yeah, we're still king of the hill there. So the relative ranking may have changed a little bit, but we're still in good shape. Now, do those various tricks that I just mentioned help? Yes. So we ran ablation studies, and I can walk you through the various pieces, but basically stacking helps, repeated bagging helps a lot. If you don't tune your hyperparameters, it's a bad idea. If you don't bag at all, it's a bad idea. If you drop your deep network, it's a really bad idea. So, and it's really a matter of, in some cases, incremental improvement rather than that, single one great, brilliant idea that, fixes it all. I think I'm running a little bit late on time. Let me go through the rest a bit more quickly, namely how to do fusion. So let me motivate it at least a little bit. So this is a data set that's actually not so uncommon. So you have tabular data, you have an image of this kitten that should please be adopted, and then there's some text description of why you should adopt this cat. And you can look at the AutoGluon tabular multimodal demo page to get more. But this is a real problem. Like if you look at an Amazon product page, well, you have title, text, numerical scores, numerical price, images, descriptions. Well, basically you have a lot of different data types. So it's not just one or two, but it's a bunch, it's a dozen. So, and you have multiple occurrences of them. So real data is really messy. And so the question is, how do we actually go and combine those pieces for a good model? This isn't the text plus tabular image captioning problem, but it's simply, hey, a lot of my covariates are differently typed, and I want to use them efficiently together. And so what we essentially settled on is that you use some very good, deep network embeddings, and then you combine them with tabular embeddings. Now that sounds really great. And if you, apologies for rushing through this, if you do this for deep networks only, well, there are those two towers and multiple towers problems. The challenge arises once you get asked the question, okay, how do you do deep fusion in a nearest neighbor classifier that's been stacked? And so part of the reason, part of the way how we approach it is we basically use, for instance, a deep network for the embeddings. We throw it through a transformer, multi-layer perceptron, a couple of pieces. Whatever comes out of this, we can then also reuse and then treat it as if it were a tabular problem, and we iterate over these. So there's still a lot of research in this area, and I think there's a couple of meaningful papers to be written. It's a very real problem, and it's one that is nowhere near as popular in publications as it is in reality. So does this thing work? I'm not going to bore you with this big table here, except that the yellow line, namely the stack ensemble works better than all the other things. And yeah, so we are onto something. So by now, I think I've convinced you that, well, we've come a long way, but there are still huge gaps. And the good thing is a lot of those gaps are eminently fixable. So for instance, there is an amazing body of literature out there on statistical testing, like two-sample tests, independence tests, and so on. They're really great. And I mean, for instance, Arthur Gretton has been an amazing source of essentially papers and algorithms on testing. The problem is, let's go and actually integrate some of those pieces into our AutoML system such that we can automatically check for shift and drift and label shift and concepts. And do we have time dependence in our data? Is it networked? What are the relevant features, explainability? All of those things people have written amazing papers about, but usually to apply this, the instructions are something like, okay, git clone this repo or pip install it, run this algorithm if the number is such and such, then do that. Now, that's great, but what you really need is you need the automation such that you can automatically, if somebody gives you a data set, say, well, yes, this is probably a time series data set. Or maybe it just has temporal drift in it. How would you go and factorize things? So this brings us back to some extent also to graphical models again. Then there's the separate issue, how to deal with graphs, how to run proper AutoML in there, how to pre-process the data, how to actually correct for data shift and drift, how to select features. And, just to give you a few mundane things that you can do, for instance, if I can automatically detect that something is text and that it's written in English as opposed to Klingon, I can just go and pull some choice English, language embeddings from, let's say Hugging Face. Or if I know that, this is financial data for some security, well, then maybe a log normal model is better than a normal model. Or, if I can identify that something's a classification problem rather than a regression problem, well, that's great too. And by the way, we actually do this to some very limited extent in AutoGluon. So when you give us the labels, we look at, how many discrete categories of labels there are. And if it's only a handful, then we say it's probably a classification problem. If it's, a lot of numbers, well, we consider that it's probably a regression problem. So we try something like this, but it's super primitive and hacky. There are a lot cleaner ways how to do it. This gets us into the entire issue of schema discovery and matching. There's plenty of work. The point is almost every real data set has those problems. And the good thing is that this is a really good place for statistics, practitioners, and also computer science to meet. Because, you have tests, you cannot probably perform all the tests, you need to optimize. There's plenty of work. Likewise, scalability, model partitioning is hard, and it's not that, hey, we are smart and you're dumb. No, it's just hard. So for instance, if I have a different server and all you have to do is just take the rounds with all the various cloud providers, or you go to NVIDIA, or you build your own GPU server, you will have different interconnect topologies. And the servers may be differently connected. And if you screw up that performance, then you can easily lose 50%. I mean, all you need to do is just, let's say pick deep speed, use the same level of deep speed and just get that split wrong. And that's because you're hitting different roof lines at different points, so stuff goes wrong. Model optimization itself is hard. So for instance, you want to use operators, you want to, integrate with other attributes. So this is non-trivial. Basically, even most dedicated teams stumble. The good thing is there's a lot of work and a lot of place out there for high performance computing, compiler builders, discrete optimization really across the pieces. and even reinforcement learning. So I'm going to conclude. I have, I think, 1 or 2 meaningful slides left. So just to say, well, this is hard. There is some progress. So over this year, we've released 4 releases of AutoGluon, and the relevant pieces here are win rate relative to the previous version. So that basically is how we measure how much better we get. And you've seen both, and you can see basically both an increase in accuracy, in speed, and in scope. And now the reason why we care about speed is because if you have more speed, you can optimize over more models and thus get higher accuracy. Now, we're just getting started. Please do join us. We have a Slack channel. You can install this. And there's a lot more to be found on AutoGluon AI. Just in case you ask, well, it's actually built on a lot of different algorithms, including and frameworks, including PyTorch. So yeah, that's just where we started. So to conclude, these are the people who did the actual work. I'm just here giving the talk, whereas they're currently sitting at their computer making the systems better. So really many, many thanks to them. And with that, thanks for having me here.
We're running a little bit over time, but I want to give anybody a few minutes to ask a question if they'd like. If you have a question, please come up to the mic so people can hear you.
So great talk, Alex. I have one question about so when we do all this stacking and ensemble, is there a consideration about the inference and deployment?
Yes. So this is the part that I skipped in the talk. And there are a number of things that you need to worry about for deployment. And so there's both latency, there's throughput, there's memory footprint. And there are a number of ways how you can address it. One is to, for instance, if you're not really hardware constrained, then it's more a matter of, setting up auto scaling and having good inference servers. And in some cases, you're in this situation. So for instance, if you're trying to diagnose breast cancer, execution speed isn't the issue, right? And you're happy to pay a lot of money if it gives you, an epsilon better accuracy. On the other hand, if you want to deploy it on a small mobile device or embedded, this matters a lot. So you will probably use something like distillation. So what you can do is you basically generate additional data sets, and then you perform function approximation. And there's a very nice bias variance trade-off there. So this is an easy thing you could do. Yep. Okay.
Alex, just a quick question. Do you think, at this point, can AutoGluon get better at the types of thing it's been doing, or is it now just applications and making it faster?
So, sorry, I didn't quite catch that. The audio was a bit off. So can you repeat the question?
Oh, I have to get closer? Okay. I think just generally, I was wondering, do you think AutoGluon can actually get better at what it's been doing now, or is it just now new applications and making it faster?
Oh, we have a long way to go to get better. There's absolutely no question. So for instance, calibration is an issue that you may want to have for your regression estimates. There's obviously always the issue. I mean, so I said in some cases, speed equals accuracy. Then there's the issue of selecting possibly suitable hyperparameters. There's the entire issue of covariate shift and drift, addressing that suitably. So I would argue getting better is going to be very much a question of being able to apply it to real problems where the data isn't just so textbook clean and tidy. There will always be new base models that we can add. There is feature selection that you need to address. Probably our biggest issue is, as said, the label leakage as we move up on the stacker. So if anybody has a great idea, talk to us, so write the paper and send us the preprint, right? So there's a lot to be done.
Thank you so much for speaking. Hopefully we can have you here in person in Houston in this next year. It was really good to meet you.
Okay.
Thank you.
Okay, good thing. Thank you.